We begin section 4.6 with a conceptual understanding of Rolle's theorem, so we can move into the mean value theorem as the actual point of Rolle's theorem. So we're kind of walking ourselves into being able to do mean value theorem. Let's see what this is about. We have f is continuous on a closed interval AB. They have a picture here for you, closed interval. I'll draw another one. So let's just choose some A here, and we'll choose B here. And if I chose whatever it is I choose for A, I need for f of A and f of B to be equal to the same thing. That's part of the condition. And it doesn't really matter what the function does from A to B, just as long as it is continuous on this closed interval. So let's just say it wiggled up and down and so we have f continuous on this closed interval, f of A equals f of B. This says that there must be at least one point C in which there is a horizontal tangent line. Oh, I've got a bunch. Jink, jink, jink. I have quite a few of them, don't I? Okay, so what if I would have, so with f of A and f of B being the same thing, I got to come back up and down to one of them. What if it was just straight across? What if I had like an A here, B? What if my f of A was here, f of B is here? And if it goes up and down it anyway, I'm going to have a horizontal tangent line. But oh yeah, well the whole thing is a horizontal tangent line. Okay, so Rolle's theorem makes sense. If you go up, you have to go down to get back to that point if it's continuous. Here they show me that Rolle's theorem isn't valid here because f is not continuous, so Rolle's theorem doesn't apply. Rolle's theorem doesn't apply here because f is not differentiable, so neither one of these cases apply to Rolle's theorem. So I went ahead and copied Rolle's theorem again for you. Our example 1, we're supposed to find an interval on which Rolle's theorem applies. F is continuous on a closed interval. I'll just go ahead and say f is continuous and differentiable everywhere because it's a polynomial. So I can pick whatever interval I want on this. My condition is my interval has to have my A and B being equal. So I could pick two level points, one here and one here. I like to make it a little easier on myself, so I'm going to pick, say, this point right here, this point right here. I'm going to choose my interval to be from 0 to 2, and I'm going to show that Rolle's theorem applies. So f is continuous on my closed interval. F of 0 equals f of 2 equals f of 0 is 0 cubed minus 7 times 0 squared plus 10 times 0. That's 0, that's nice, equals 2 cubed minus 7 times 2 squared plus 10 times 2. It's like 8 minus 28 plus 20. That's equal to 0. Therefore, I have f is continuous and differentiable everywhere on my closed interval with f of 0 equaling f of 2. So let's see if there's one point in that interval such that the derivative is 0. I know where it is because I can see the graph of it now. I bet you it's going to be right in there somewhere. Don't exactly know where it is. Kind of looks close to 1 but not exactly 1, so let's just see. F prime of x equals 3x squared minus 14x plus 10. I need to find where this is 0. I look to see if it will factor. You will not factor, so I will have to use the quadratic formula, which is lovely. X equals minus b plus or minus square root of b squared minus 4ac all over 2a. Chunking that in and putting in your values, you will end up with x, oops, not x, with, sorry about that, after it's simplified, you should get 7 plus or minus square root 19 all over 3. In other words, this is about 0.88 and 3.79. Is one of these values in between my interval? Yep, that little boy is. So C equal 0.88 is my C, because f prime of 0.88, if you plug in a 0.88 into, or the approximate, you should get 0. Therefore, Rolle's theorem has been verified. It works for this one. Alright, the mean value theorem is used in a number of proofs that we have, well, we've just kind of bypassed. We believed the theorem and then we said we'll look at the proof of it later. The mean value theorem, I have to have, I just chose the function we had last time. I just have some f continuous on a closed interval. So I'll pick a closed interval, say from, do I have any restrictions? Nope, I don't have any restrictions on f of a and f of b this time. So I can just pick wherever I want to. I'll pick right here to be a, and I'll just pick right here to be b. So there's my a and b. We know that it's differentiable and continuous here. That says that whatever the slope is between your a and your b, that's what this part is saying right here. You've got some sort of slope between your a and your b. There's a difference in the y's and the difference in the x's. There's got to be at least one tangent line such that it has that exact same, so I'm looking, looks like right about here has one. If you'll notice, a tangent line right here kind of has that same, and I think right about here has the, oops, I went up on that, has about that same slope. And it doesn't matter which 2 points you pick. Let me pick another pair. So let's pick one that's kind of a steep line. Let's choose these 2 points here. So here's my slope in between those, that a and b point that I picked. This mean value theorem guarantees there's another, oh, there it is right there, I see him. There's a tangent line somewhere else, and up right in about here would be another one where there's a slope that's identical to that slope. That's what the mean value theorem means. Alright, I've drawn a picture for this particular problem. We've got some sort of meteorologist, and he's concerned about whether or not we've got favorable conditions for thunderstorm or tornadoes. And whenever the lapse rate rises above the 7 degrees Celsius per kilometer, then we might have that occur. We know that the temperature and the altitude we have at that particular point at 2900 we have 7.6 degrees Celsius, and at 5600 in altitude we have this temperature of negative 14.3 degrees. Well, let's figure out what the lapse rate is by doing the change in y's over the change in x's. So let's just get that lapse rate and see what it is. Minus 14.3 minus 7.6 all over 5.6 minus 2.9. This gives us negative 8.1 degrees Celsius per kilometer. So we know that this is rising, we know that the lapse rate has risen above this 7 because it's changing at a greater rate than that. By the mean value theorem, I know that that is occurring at other places because I don't know I know that this might have done this in a linear fashion, but it might have also done something like this as it went from one place to the other. And that slope right there is that negative 8.1, and I know that that has to occur by the mean value theorem. That has to occur in more than, so let's put another one down. That has to occur in more than one tangent line. That might be here. I know it occurs at least once because the only way it could get from one point to the other without doing more than one would just be a straight line, and then that would be the occurrence of one here. I've got one there, I've got one happening here, I've got one happening here, and I have one happening there as well. So I see that I have at least more than one occurrence of this, so I can be concerned about the likelihood of increased storms. I plotted for you with my calculator this function on the interval -2 to 2, and then the y's are just on a scale of 1 point each. So I'm supposed to verify using the mean value theorem that we have an occurrence of this particular case. Alright, let's do it. F is continuous on a closed interval AB. Alright, F is continuous and differentiable on -2 to 2 because F is a polynomial and is continuous and differentiable everywhere. So my conditions are holding. Therefore, we know, since I have all of the conditions on the front end in the if part, then there must be at least one point C such that this will happen. So I know I have that point. I just have to go find it now. F prime of x is, drop my 3, so that would be 6x squared minus 3. I need to find the place where this derivative equals the slope. So what is f of a and what is f of b? I need to go get those values. Alright, I got the y values. Now I need to do the f of b minus f of a over b minus a. Plug those in, see what I get. Alright, I found the slope between those 2 points. It's 5. So there has to be some place that the derivative equals 5. So I've got to figure out where, whoops. Alright, I get x equals plus minus square root of 4/3. That's going to be about plus minus 1.15. This tells me that I have 2 points in this interval. One at 1.15, which should be right around in here, and another at negative 1.15, so right around in here somewhere. So let's get these lines and see if it looks like, yeah, it does look like it's right around in there. Get the other one. Yep, there they are. lovely. Alright, I've written the mean value theorem result up here as long as f is continuous and differentiable on that interval AB. So one of the consequences is, we know that if it's a constant, then its derivative is 0. We know that way, but it also implies the converse of this by the mean value theorem, because if f is differentiable and we know that the derivative at all points is 0, that means the derivative at all points is 0 by the mean value theorem equals 0. That means that the difference between the y values also has to be 0. I'm just going to multiply this. I'm going to choose two different b's and a's. So if I multiply both sides by b minus a, that's gone, and then it's going to imply that f of b equals f of a, meaning that here's you an a, here's you a b, f of b has to equal f of a, so no matter where I put this dot, this one has to be above, and the slope between those two is 0 at all points on that interval. For this next theorem, I have two functions f and g, and no matter what x I pick, they always have the same slope at that point, meaning that they're always increasing or decreasing by exactly the same rate for all x on that interval. Then we would know, because of this, f of x minus g of x would be a constant. Because no matter what I do, if I have this function f, and let's just say that this is f of x, the slope on f always equals the slope on g, meaning they're always increasing or decreasing by the same rate, and nothing else differs about them. Then, if I subtract these two, I will get that same constant. They will differ by that exact same amount. I've drawn a picture here that satisfies an interval of increase. So if this is some a and then this is some b, if the derivative is always greater than 0, or the slope is always greater than 0, no matter where I pick, then that means it must be an increasing function. And likewise, if I look at the other flip side of that coin, if the derivative or if the slope is always less than 0 or a negative slope, then it is a decreasing function. And that sums up section 4.6. See you at the Collaborate.